Now that we have covered the basics of descriptive statistics, it is time to move on to inferential statistics. Inferential statistics refers to methods that rely on probability theory and distributions, in particular to predict population values based on sample data. While these definitions may not be completely clear, just yet starting from the next lesson we will define what a distribution is and we'll go through a couple of the distribution. You will likely use that work. This will naturally lead us to the point estimates and we will conclude the section with confidence intervals. We will not only present these topics but will also develop a deeper understanding of the statistical processes. This will help you a great deal if you decide to get into data science. I recommend that you complete all the exercises provided as they will reveal additional subjects. You will be in charge of researching. These insights will likely be your gateway to the fundamentals of quantitative research and data-driven decision making. In this presentation, we will embark on a journey to explore the concept of distributions and the ubiquitous normal distribution in statistics. Distributions are the foundation for understanding how data is spread out. The normal distribution, also known as the Gaussian distribution, is a bell-shaped curve that frequently appears in various real-world phenomena. By understanding these concepts, we can unlock valuable insights from data and make informed decisions across numerous disciplines. Imagine a collection of exam scores. A distribution portrays how these scores are spread out. It does not just tell us how many students got each score, but also the likelihood of encountering a particular score. There are two main ways to represent distributions: frequency distributions and probability distributions. Frequency distributions showcase the number of items each unique value, score in our example, appears in the data. Probability distributions, on the other hand, delve deeper, indicating the chance of encountering each value within the dataset. In statistics, when we talk about distribution, we usually mean probability distribution. Definition informal: a distribution is a function that shows the possible values for a variable and how often they occur. You can understand the Wikipedia distribution. Examples are normal distribution, student state distributions, Poisson distribution, uniform distribution, binomial distribution. The beauty of distributions lies in their versatility. They can morph into different shapes depending on the nature of the data. Histograms are champions at visualizing continuous data, like heights or exam scores. They depict the frequency of data points falling within specific ranges, forming a visual representation of the distribution shape. Bar graphs excel at showcasing the frequency of categorical data, such as hair color or brand preference. Each bar presents a category and its height corresponds to the frequency of that category within the data. Pie charts come in handy when presenting data in proportions. Each slice of the pie presents a category and its size corresponds to the proportion of data points belonging to that category. Now let's come to the star of the show, the normal distribution. The ubiquitous bell-shaped curve depicts a continuous probability distribution. Imagine a weight distribution of a population. The normal distribution tells us that most people will have weights close to the average weight mean. And as we move further away from the average in either direction, lighter or heavier, the probability of encountering those weights become less likely. The normal distribution is symmetrical, with the peak at the center representing the most probable value, which coincides with the mean. The farther we move away from the mean, the lower the probability of encountering those values. The total area under the curve sums up to 1, signifying the certainty that a weight value will fall somewhere within the distribution. The statistical term for it is Gaussian distribution, but many people call it the bell curve as it is shaped like a bell. It is symmetrical and its mean, median, and mode are equal. If you remember the lesson about skewness, you would recognize it as no skew. It is perfectly centered around its mean. Alright, it is denoted in this way and we stands for normal. The tilde sign shows it is a distribution and in brackets we have the mean and the variance of the distribution. mean and the variance of the distribution. You can notice that the highest point is located at the mean. This is the highest point. This is located at the mean. Yeah, or this point is located at the mean. Because it coincides with the mode, the spread of the graph is determined by the standard deviation. Now let's try to understand the normal distribution a little bit better. Let's look at this approximately normally distributed histogram. There is a concentration of the observation around the mean which makes sense. It is equal to the mode. Moreover, it is symmetrical on both sides of the mean. We use 80 observations to create this histogram. Its mean as 743 and its standard deviation is 140. Great. But what if the mean is smaller or bigger? Let's zoom out a bit of adding the origin of the graph. The origin is the 0 point. Adding it to any graph gives perspective, keeping the standard deviation fixed or in statistical jargon controlling for the standard deviation. A lower mean would result in the in the same shape of the distribution, but on the left side of the plane in the same way. A bigger mean would move the graph to the right. In our example, this resulted in two new distributions, one with the mean 470 and a standard deviation of 40, and one with the mean of 960 and a standard deviation of 140. Thank you so much. Please subscribe and share the channel for more contents.